Let's have a look at question 7, a difficult question here. We've got to fill in the rest of this mechanism. Let's have a look at this here. We've got a lone pair of electrons and an oxygen, and we've got an H+. There's a good chance that the arrow will go from the lone pair to the H+ and form a bond between the two. When it does so, we're going to make this, and the OH will bond between the O and the H, or make OH2. Where will the plus be? Well, the plus will be on the O, because that has had electrons move away from it, with the curly arrow going from the O to the H+. The H+ will lose the plus charge. Plus charge will be on the O, because electrons have moved onto the H and removed the H+ charge. So here, curly arrow to the H+, and the O gets the plus with an H2. What's next? Well, if you look at the next one here, forget that curly arrow, look at the next one that's given to you. It's got a plus charge on this carbon here, and this OH2 plus has gone. So how do we get rid of that OH2 and end up with a plus charge here? Well, this bond's got to break, and the electrons go onto that plus charge. It will release H2O then. The plus charge will disappear, release H2O, water, because the electrons have gone on to the O+, and so electrons being minus have eliminated that plus charge on there. This carbon now is short of the bond that was there. It's not got the bond that was there, so it's not got enough bonds. If it's not got enough bonds, it's got a plus charge on it. How does this then turn into this? Well, this H here that's been drawn for you has disappeared from here. It's gone, and so is the plus charge, and there's a double bond here. So clearly this H has got to break off, and which way will the electrons go? They'll go into here rather, and make the double bond. So they move from here to here. That will release the H as a H+. Make a double bond here, and then this carbon that hasn't got enough bonds has now got an extra bond and has got rid of the H+. Draw a structure of a different cyclic alkene formed from D. So formed from D, how could that work? Well, what could actually happen is, instead of this H breaking off here, why doesn't one of the H's here break off? So there's no reason why that H should break off from this carbon. We've got another carbon to the other side of the carbocation, the plus charge, here. So there's no reason why one of the H's here and H here couldn't break off. That H could stay, and one of these H's could break off and form a double bond here instead. So why is a H from here, from this carbon breaking off, why doesn't a H, instead of from there, why doesn't a H come from here and break off and form the double bond there? So the double bond could be here instead. (7.3) Let's have a look. Carbocation D can form a reaction called a rearrangement to form carbocation E. So this can turn into this. A hydrogen atom and its bonding pair of electrons move from A to carbon B as shown in figure 2. In other words, the plus charge moves. So why could the plus charge move? Why would the plus charge move? That's what the question's asking. So it's rearranged somehow. It's not asking you how it's rearranged, it's asking you why it's rearranged. Well, let's have a look at this plus charge here. This carbon here on this corner has got a carbon down here and a carbon here. A carbon either side of it. So this C+, a carbocation, has got a carbon here to one side and a carbon here to the other side. This carbon with the plus, the carbocation, has got two carbons, one either side. It's a secondary carbocation. Secondary means that there's two carbons joined to the, bonded to the C with the plus. Whereas here, this carbon has got one carbon here, and 1 carbon here. It's got 3 carbons joined to the C with the plus. So the carbocation's got 3 other carbons joined to it. It's a tertiary carbocation. In other words, this is a secondary carbocation, this is a tertiary carbocation. The tertiary carbocation is more stable than the secondary carbocation, and that's why it's formed. So the question isn't asking how this rearrangement's happened, it's just simply asking you to recognize that this is a secondary carbocation, this is a tertiary carbocation, and the tertiary carbocation is more stable than the secondary carbocation, and that's why that happens. As a result of this rearrangement, a third alkene is formed from this reaction. Draw the structure of this third alkene. So what could actually happen is, from here, how does this plus disappear? How do we get rid of this plus? So what could actually happen is, this H could break off and go into a double bond between the two. Or the alternative is that one of these H's could break off and form a double bond here. So one of these 3 H's could break off and form a double bond here. That would get rid of that plus, because you'd have an extra bond. So this carbon now would have enough bonds, 4 bonds. At the moment it's only got 3 bonds. It would now have 4 bonds, so it would get rid of the plus. And one of the H's here would break off and release H plus and get the double bond in between the two here. And then finally, cyclohexene is prepared by the dehydration of cyclohexanol, concentrated phosphoric acid, which is there, cyclohexene, cyclohexanol, and phosphoric acid are the catalyst. So you're not asked for any kind of reaction, you're just asked to identify the boiling points of these 3 and how cyclohexene can be separated from the reaction mixture. Well, this is phosphoric acid. I've drawn for you cyclohexene. So hex is 6, cyclo in a ring with an ene, a double bond, and cyclohexanol is 6 carbons in a ring with an OH in there as well. So you've got to identify which has got the largest boiling point. So the largest boiling point happens when you've got intermolecular hydrogen bonds. Oxygen joins to hydrogen, or fluorine joined to hydrogen, or nitrogen joined to hydrogen. So I've got 1, 2, 3 oxygen to hydrogen bonds. I'm going to have intermolecular hydrogen bond in between one of these phosphoric acid molecules and another. I'll get a very large delta plus delta minus polar bond on the OH, and that will form very, very strong dipole-dipole attractions with the other polar bonds in the other 3 OHs on a neighbouring phosphoric acid molecule, and those very, very strong dipole-dipole interattractions when you've got an oxygen joined to a hydrogen, a fluorine joined to a hydrogen, a nitrogen joined to a hydrogen, that's called hydrogen bonds. Very, very strong dipole-dipole. Plus the fact that we've got a phosphoric acid to an oxygen as well. This is going to be a polar bond, and so that's going to also form dipole-dipole attractions. This will have the highest boiling point because it's got hydrogen bonds in it, and it's got 3 OHs, so it'll have 3 sets of hydrogen bonds, and it's also got a polar bond here, the phosphorus to the oxygen, which will form dipole-dipole attractions. Next boiling point, next highest boiling point is this one, because it's got hydrogen bonds, but it's only got 1 OH, so it'll have 1 set of hydrogen bonds between the molecules. This one has only got carbons and hydrogens, so it's got no hydrogen bonds, it's got no polar bonds, it's going to have van der Waals bonds as intermolecular bonds, which are the weakest kind of intermolecular bonds between its molecules. So we've explained that. Explain how cyclohexene can be separated from the reaction mixture. So what you're going to use is distillation. You might use fractional distillation because you've got a mixture of 3 different liquids. So fractional distillation or distillation to separate liquids with different boiling points.